Directional boring, commonly called horizontal directional drilling or HDD, is a highly effective method for installing pipes and conduits under the ground from the surface with minimal impact to the environment surrounding the project. When trying to encompass the history of horizontal directional drilling, it is only appropriate that we start with a man who many veterans of the industry have come to recognize and respect as the father of HDD, Martin Charrington.
I started my own business in 1964 as at that time, a utility drilling boring contractor in an area that had no footprints or blueprints or anything like that, in a kind of a area that's no man has ever been before. And there was no steerable tools like that. You didn't steer it across. You didn't have any idea where you was at. There was no survey system. It was kind of a drill straight from point A to point B. And I thought, well, you know, I've always been fascinated with the oil and gas industry about their ability to do directional work. But it took a long time to develop the process because we didn't know what is it supposed to look like. There was no blueprints. At that time, of course, that was way early on, and there was no surveying equipment, and there's no steerable methods to these drill bits like you see with present-day equipment in the utility industry. Everyone wanted to do 10,000-foot cross, and that was just, it's mind-boggling. Well, those are done. Those are done now, especially on certain types of pipes, especially on this, what they call intercept type work that's done, where you drill from both ends and they meet in the middle. Better surveying, straighter holes, better drilling fluid mixtures and management and everything, better conditioned holes. That's going to be longer bores, bigger diameter, less damage to the pipe, less damage to the coating, more mixed formations, being able to drill in that a little bit better. I see those things, it's going to come. Those things will come.
Directional boring is an effective method for installing telecommunications and power cable conduits, water lines, sewer lines, gas lines, oil lines, product pipelines, and environmental remediation casing. This no-dig technology can be the perfect solution when crossing waterways, roadways, congested areas, environmentally sensitive areas, and areas where other methods are too expensive or not feasible. Directional boring is used in place of other techniques for many reasons, including less traffic disruption, lower cost, deeper and longer installation, quicker completion, where directional capabilities are the only option, and it is safer for the environment. To date, installation lengths of more than 12,000 feet have been completed using horizontal directional drilling. Directional boring machines are rated by pullback force and range from a small machine with a few thousand pounds of pullback to the largest machines with over 1 million pounds of pullback force. The process begins when a directional boring machine hydraulically pushes a bore head, which is connected to a hollow pipe, into the ground at the entry point at an angle. A pressurized jet of fluid, also called drilling fluid, flows from the bore head, which is then used to cut through the ground. As the bore head cuts, additional joints or sections of drill pipe are continuously added as the bore head is pushed toward the exit point. The drilling fluid is generally a mixture of naturally occurring bentonite clay and water. Additives are sometimes used to improve the performance of the drilling fluid, and in special cases, inert polymers are used instead of bentonite. The drilling fluid is pumped down the borehole through the hollow drill pipe and is used not only to cut through the soil, but also to facilitate the removal of cuttings, stabilize the borehole, cool the cutting head, and lubricate the passage of the drill pipe. Drilling fluids hold the cuttings in suspension to prevent them from clogging the bore. A clogged bore creates back pressure on the cutting head and slows production. The cuttings are carried back to the surface, where they are either allowed to settle out or to be removed mechanically using the mud cleaning system. The drilling fluid is generally classified as non-toxic and can easily be disposed of along with the cuttings from the borehole. This is usually accomplished by land farming, whereby they are returned to the surrounding environment. While boring, since the drill head is under the ground and not visible, it is extremely important to track the location of the drill bit in order to keep the borehole on target. This is done using a locating system. The locating system provides real-time information about the drill bit location, such as depth, angle, and direction. The most commonly used locating system for shallow depth applications is called the walkover system. Where deeper depths are encountered and higher accuracy is required, systems common in the oil field are used, such as the magnetic guidance system with wireline grid systems. The most recently developed gyroscopic system does not require any surface access or surface wire grids and is not affected by any external magnetic interference. Deep drilling horizontal or directional depths have reached as much as 500 feet using the magnetic systems. The gyro systems have unlimited depth capabilities. When the walkover system is used, the operator of the locator walks along over the path of the bore, directly above the drill head with a receiver. A transmitter, called a sonde, which is located in a recessed compartment directly behind the bit, sends continuous data to the receiver through an electromagnetic signal. The receiver displays the data, which is then read by the locator. The locator uses this information to tell the drilling machine operator by radio and/or through a series of hand signals where the bore head is located and if any changes in the drill path need to be made. For deeper bores, and when conditions do not allow a receiver to be positioned over the bore path, or if interference degrades the signal, a wireline system is used. The most common type of wireline system is called the magnetic guidance system. This system uses an actual wire that is fed through the drill pipe to a tool that measures the location of the bit and transmits the data to the surface. At the surface, the data is recorded by a computer and relayed directly to the drilling machine operator, who makes continual adjustments to the bore path based upon the data provided. To compensate for potential man-made and naturally occurring magnetic interference, an artificial electromagnetic grid can be deployed at the surface as a secondary tracking method used in conjunction with the magnetic guidance systems. These systems are widely used on bores in excess of 200 feet. When deeper bores are required or surface conditions dictate that conventional walkover and wireline systems are not feasible, the gyroscopic steering system is used. These highly accurate systems depend solely on the Earth's true magnetic north and are not affected by any man-made or naturally occurring magnetic interference, which can adversely affect the accuracy of the other systems. These gyroscopic steering systems therefore eliminate the need for all surface access above the bore path and provide zero impact to the environment surrounding the bore path. The type of drill bit to be used depends upon the condition of the soil. In softer soil, an angled jet bit that sprays drilling fluid is used. Boring straight is accomplished by continuous rotation of the drill pipe as it is pushed into the bore hole. Steering is accomplished by stopping the rotation of the drill pipe, realigning the angle of the bit to the desired direction, and applying forward thrust to the pipe. The directed jet of fluid and forward thrust cuts a new path in the desired direction. In harder soil and rock, the bit is often connected to a mud motor. Drilling fluid is pumped down the drill pipe to the mud motor, which converts the hydraulic flow and pressure of the fluid into a mechanical rotation and torque, which then rotates the bit. In this situation, it is not necessary to rotate the drill pipe to direct the bore path. Steering is accomplished by rotating the angle of the mud motor to the desired direction and applying push. In cases where the ground is unstable, a washover pipe or casing can be pushed down the borehole to prevent the collapse of the whole wall. Some directional boring systems use a dual pipe exclusively. Upon reaching the exit point, the locating system and bit is detached. If the borehole needs to be enlarged, the end of the drill pipe is attached to a reamer or hole opener. The reamer is then pulled back towards the drilling machine while rotating the drill pipe with as many consecutive passes as necessary. In most cases, drill pipe is added behind the reamer or hole opener so that there is always a drill pipe in the borehole. In some cases, two boring machines may be used, one to pull the pipe and one to push it from the opposite end. When the borehole is approximately 25 to 50% larger than the product pipe to be installed, the end of the drill pipe is connected to a reamer, which is then connected to the product pipe and a swivel, and pullback commences. Another popular process for replacing pipes, called pipe reaming, can be used in place of pipe bursting. Pipe reaming uses a directional boring machine to pull a reamer through the old pipe and causes no disturbance to the surface. Directional boring has evolved steadily since the 1970s, with new tooling techniques constantly being developed. Intercept boring is one such technique, where two machines bore from opposite directions and their respective boreholes meet in the middle. This enables longer bores to be completed sooner than would be possible with a single machine. However, this requires highly precise, continuous bore head locating. Another new method, direct pipe, uses a micro-tunneling boring machine known as an MTBM, with the final casing installed behind the MTBM. This method enables boring in unstable and challenging soil conditions, while retaining the benefits of directional boring. Combining micro-tunneling with directional boring eliminates the need for costly vertical bore pits required in conventional micro-tunneling or auger boring operations. Directional boring is generally less expensive than other trenchless methods such as jack and bore and micro-tunneling. With continuous new technological development and increased popularity, directional boring costs are now lower than ever. In urban areas, directional boring can be more cost-effective, safer, and less time-consuming than open-cut trenching. Directional boring is fast becoming the preferred method for many installation applications. Projects once seen as impossible are now easily accomplished with directional boring.